Hello guys, welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easier to understand. Today, a simple problem on the introduction of the second law. Here we have a little drawing of a system. We have an engine, heat engine, HE for heat engine, that is gaining some energy from a hot source and outputting some energy to a sink. And with that, it outputs some work. Right? Now, we know that first law of thermodynamics tells us that if we do an energy balance on this heat engine, that whatever is going in, that is this energy here, has to be equal to these two guys here, right? However, the second law is more interested on the quality of energy, how much actual useful energy in the form of work we can obtain from a given source. So this simple problem reads like so. A heat engine with a thermal efficiency of 45% rejects 500 kilojoules per kilogram of heat. How much heat does it receive? Okay, so pretty much this is saying that this rejection over here is for 500 kilojoules per kilograms. Okay, we don't know this, we don't know the work output, and we don't know how much heat it receives, but we do know its efficiency is 45%. And in spite of this, this is a very simple question in the solving of it, but I would like you, when you solve this, I would like you to have this as a very intuitive solution, not something that you need to look up formulas or equations to be able to solve, but just by thinking about it, right? What is the efficiency? What is this guy here, the efficiency? It's how much you get out, right, in respect to how much you're putting in, right? So the efficiency is what we get out. Let's put this as useful to how much you pay for, right? How much you put in. In this case here, what we're putting in is exactly the energy that's coming from the furnace, right? That's what we are paying for. That's the quality energy that's going into our heat engine. And what we're outputting is this 500 kilograms per kilogram, kilojoules per kilogram, which is not useful, and this useful work here, right? So if we talk about it, if we convert that into the equation, what we're saying is that the useful thing we want out of this is work. So work output is the useful energy that's coming out of this heat engine. And what are we paying for that? Well, we're paying with high quality energy that's coming from a hot sink. So in this case, we usually call this QH for hot, and then this one here, QL or QL for low, right? So this can be QH for hot, QH for high, and QL for Q low. And then obviously this is the amount of energy we have. So if we can convert all this energy here into useful work, then the efficiency would be 100%. That unfortunately is not possible, according to what Carnot told us, right? Nicholas Carnot, I think it's Nicholas. He told us that you need to have a heat sink. So in other words, you can't transform all this energy into useful work. There needs to be a part of energy that goes to the sink, right? Part of energy that's rejected. Okay? But we can apply the first law of thermodynamics here. We can do a little energy balance on our heat engine, right? So if I do energy balance on the heat engine, so this is my control volume here. We see that all the energy going in and coming out has to be balanced out. So what's going in? Well, Q hot is going in, and then what's going out? Q low is going out, and work is going out, and that has to be equal to 0. Okay, so if we apply that to this idea of efficiency here, we can substitute where we have work, we can substitute that by the relationship from the first law, right? So work from this definition here is just my Q high minus my Q low. So I can do this. So this is equal to Q high minus Q low divided by Q high. Okay, so if this is Q high on both ends, so we can divide there and we'll be left with Q low over Q high. So just the ratio between the two, right? And we know that the efficiency for this given problem in particular is 45%, right? So 45%. Okay, so therefore this here has to be equal to 45%. And we happen also to know how much is rejected, right? This is the amount of heat rejected, and that is 500, right? 500. So that means that our only unknown in this equation, in this particular equation, is the heat from the heat source, which is precisely what we're looking for, right? So we can solve this in. You can also think of this, if you want to, as Q in and Q out. So it'll be the same thing as writing it 1 minus whatever is Q heat being rejected, Q out, divided by whatever Q is going into my system. Okay, so let's just solve this quickly. Q in will be equal to Q out 1 minus 0.45. So that means that this is equal to 500 divided by 0.55, and this is equal to 909.099909090999. It keeps going. So just kilojoules per kilograms. Okay, that will be our answer right there. Unit-wise, obviously the unit, where were we? Over here. Okay, obviously the unit of this guy here has to be the same as this guy here, because they need to cancel out because we have percentage on this side. So it's just a ratio. It's a ratio between the two things. So as long as we're putting this guy as kilojoules per kilogram, then that means that when we find this fellow here, it also has to be in kilojoules per kilogram. So that's why we have this unit here. Okay. Now what I want you to take away from this is, like I said, a simple problem. It's not meant to be hard, but I want you to take away is these definitions, right? Note that we're applying second law principles, but first law still applies, right? The idea that we cannot create or destroy energy is still everywhere. Second thing is efficiency, right? What we're getting out in respect to what we're putting in, okay? So another way to do it, it's precise like that. So what we're getting out, useful thing getting out, divided by what we have to put in, okay? Useful thing going out or being outputted in respect to how much we're paying for, how much energy we're paying for. If you have this definition in mind, it's going to help you out, because later on when we change systems, when we have refrigerants or ACs and things like that, we still need to, if we have this definition in mind, it's easy for us to translate that into mathematics. But if we are memorizing stuff, and we're memorizing, for instance, this relationship here, then we're going to have problems later on. Okay, so hope this was useful. If it was, let me know. Subscribe to the channel so you're always up to date with our latest problems, and leave any comments or any questions that you may have down below.